always we try to represent the problem using a matrix A, and we know that matrices are very good tools to represent linear transformations, any kind of transformation, including even the derivatives of or the differentials of certain variables. So from A, we identify A minus lambda I, we find the determinant, we get the characteristic polynomial, we find eigenvalues, the eigenvectors, we construct a matrix P composed of the eigenvectors, and then we should also notice that for a matrix A, which is n by n, then we need, if this is n by n, then we need P n by n, which means that we have to have n eigenvectors, okay? And then from this P, we can find how we can transform vectors from one domain to the other. And if the vectors are transformed in this way, assuming that here we have x and here we have the vector u, we can also have a vector x0 and we can have a vector u0. And with u0, we mean a vector which is u0 at initial time. Then we can find how xt can change as a function of time again. And this is also how ut can be a function of time and might depend on u0 or might depend on the initial condition. Now, so this is how u and x change. This is the expression how the d is related to the matrix A. And here, this also means that d it is similar to A. And D being similar to A is any matrix which can be represented like this. This D, two matrices don't have to be diagonal to be similar to each other. We've talked about this one before. And now, so the most important or the most essential relationships is the vector transition from one basis to another, and the matrix transition. How a matrix or how a linear transformation can be projected onto different bases. Now, if we see here, we know one thing that any vector x1 can be equal to xa times x0, right? What this means is that we can start with a vector x0, and we know that this x0 can be rotated, or the magnitude of the vector can change if we multiply it with the matrix A, okay? And here, we can also have a similar relationship. So now, this problem here, the equivalent discussion or the equivalent treatment of this problem in the new basis is the following. We have u1 is equal to d times u0, okay? And again, we can say that u1 is also written as what would it be? This would be p inverse u1 would be equal to p inverse times x1. Okay, so this is how they move around, and again, x1 is equal to p times u1. So we should remember all of these relationships, and then we should use these when we solve different problems. And now, before we go into more advanced applications, I just want to say a few words about the powers of matrices. Okay, powers of matrices. Matrices. So a matrix D, the diagonal matrix D, this is equal to P inverse A times P. If we multiply it from both sides of the equations PD, this would be equal to P inverse AP. And then the P times P inverse, this gives an identity matrix. So we get that PD is equal to AP. And then we can multiply from both sides, from the both right side, and we can obtain the following. PD P inverse, this would be equal to AP P inverse, okay? And then this gives again an identity matrix, so we can obtain the following. We can get that A, the matrix A, is equal to P D P inverse. So if we want to calculate what is A squared, this one would be equal to PD P inverse times PD P inverse. So now when we look at this, we can remove these signs and we can consider the multiplication of these two. And here we get PD dP inverse, which would make this PD squared P inverse. Because the P inverse times P, this is equal to the identity matrix. Okay? Identity matrix, which is a diagonal matrix where all the entries are equal to 1. So now, similarly, we can write that A is equal to P d cubed P inverse. Or, if we generalize this a little further, we get A to the power n. This is P e to the power n P inverse. Now, why do we need this? This is useful because anytime we multiply two matrices, this takes time. Okay, this is computationally expensive. If you are in an exam, it will be relatively difficult to take. So let's assume a matrix, which let me pick up a specific matrix here. Here I have 1, 7, 2 minus 15 minus 4. So this is 7, 2 minus 15 minus 4. Now this is the matrix in the standard basis. Okay, this is how it looks like. And the diagonalized version of this matrix is 1, 0, 0, 2. So now the question is, if you are in an exam, which one can you find the square faster? You have to calculate the square of this matrix, which means that we are going to multiply this one with itself, and it might take some time, but the square of the diagonal matrix is equal to 1, 0, 0, 4. Okay? This is easier, relatively easier. If you want to find the cube, this is going to be 1, 0, 0, 2 to the power 3, this is 8, fine. This is it. So this is equal to d cubed, this is equal to d squared. But now, here, we need to do quite a few calculations. 7, 2, minus 15, minus 4, and here we get 7, 2, minus 15, minus 4. Let's multiply these two together, and we can. So let's separate this one like this. 7 times 7, what is 7 times 7? You can hear the talking about the multiplication table even in Albanian parliament. So what is 7 times 7? 7 7.
48.
48. Is that the Kosovo version of multiplication table? No?
Yeah, the new numeric system.
Okay, that's good. Here's 42. So here we have 49 minus 30, whatever this is around 19. And then here we get 7 times minus 15. What is 7 times minus 15? This is 70, 35 minus 105 plus 30 minus 75. Then 14 minus 8, we get 6, minus 30 plus 16, minus 14. Okay, that's good. So this is our a squared. It took some time. We even had debates with Kosovo multiplication table and Albanian multiplication table. Here we have it. Now the a cubed, it might take some more time. So in principle, it looks like calculating the power of a specific matrix, it might be useful, especially if we are considering very high powers of the matrix. So now, and again, what we can do next is also we can calculate how much time it takes for a computer when we multiply two matrices. Let's assume for a moment, if you have a matrix which is A n by n, if we multiply this one with a matrix which is B n by n, and this would be equal to another matrix which is C n by n. And in principle, we know that in order to get any element in this matrix C, how many calculations do we need to do? So this is the matrix A, this is the matrix B, and this would be the matrix C. And in this case, let's assume that we need to multiply this row of A with this column of B. How will the multiplication follow? Each element in here will multiply each element in this row. We multiply an element in this column. Then we have this, and then we have this times this. Okay. So if this is n by n, each element in C each element in C. So let's say C, let's call this one 4, 3, okay? Well, this might be, I just want to see that I pick out the C in the 4th row and the 3rd column, but in principle this element will include n multiplication, okay? N multiplications and n minus 1 and minus 1 additions. So only to get a single element, we need 2n minus 1 calculations for a single element. But if C is composed of n squared numbers, then the total number of calculations, 2 multiply 2 matrices, which are n by n, is going to be n squared times 2n minus 1. So this is equal to 2n cubed minus n squared. Okay, so this is the number of calculations which is needed to do whenever we multiply 2 matrices. Imagine now that we have a cell phone camera that has 1 megapixel resolution, and that is composed of 1,000 rows and 1,000 columns. So this is 1,000 rows and 1,000 columns. So it is 1,000 by 1,000. So imagine for a moment if n is equal to 1,000. So then, how long does it take for your computer to multiply 2 matrices? This is a good question. So n is equal to 1,000. Then the question is this: find time. Okay, how do you do it? You know, you are taking linear algebra, and you know that the number of calculations is going to be equal to 2 times 10 to the power 3 to the power 3 minus 10 to the power 3 all squared. Okay, so this is the number of calculations, and we have to divide this one by the number of calculations that the computer can do in 1 second. How many calculations can a computer do in 1 second? So what is the speed of your processors? Who can remember a common speed of a processor? Such gigahertz can a computer do. Albino, what is a common processor speed?
Let me guess.
Say it again.
Let me guess. Just let me search it.
Professor, mine, for example, has 1.8 gigahertz.
So 1.8 gigahertz is something like this. So this is going to be 1.8 times 10 to the power 9. This would be the number of calculations per second. So this would be equal to 2 divided by 1.8. So this is approximately 1. Okay, this stays here. Multiply 10 to the power 3 minus 10 to the power 3. This is 10 to the power 9. So this is 10 to the power 9 divided by 10 to the power 9 minus 10 to the power 6 divided by 10 to the power 9. Okay? So this is, it looks like it would be something 2 divided by 1.8. So this is 1.1 times 1. So this is 1 second. This is 1 second minus 1 millisecond. So this is going to be equal to 1.1 times 999 millisecond, okay? Or approximately 1 second. So it takes 1 second to multiply 2 matrices which have a dimension of 1,000, 1,000 by 1,000. Now, this is the use of the diagonalization whenever we want to use powers of matrices. Now, let's have a look at an example. Let's assume that we want to solve a problem which evolves in time. Okay, a problem that evolves in time. They can be called with different names, but one of the names it would be difference equations. And a good example of how certain quantities can evolve in time would be, for example, the number of viruses that can be in air, okay, or bacteria. Now, nowadays that we are we have a more common global knowledge regarding the viruses, we can give these examples. But this is not true for all the parts of the world. We are kind of new to this. But certain parts of the world, they were accustomed to the terminology of virus spread. Okay. Now this became a little more global. So now we can provide examples like this. Let's assume that the number of viruses x is equal to a times x0, where x0, this is the number of viruses or bacteria at time number of virus at time t equal to 0. Okay, and then we assume that each time at any time frame they multiply with a factor of 2. Okay, so this is the input. We start with a certain x0 number of viruses, and the multiplication factor is 2. So then we start with 2. After a day, they become 4. After another day, they become 8. After another day, they become 16, and so on. So
the board isn't that clear. Maybe it's because of the internet connection.
I don't know if you are the only one. It could be you. How do you see the board? Is the board clear?
Blurry. It's kind of blurry.
Can we have a second one confirming this issue?
For me, it's clear.
It's also okay for me. I see it clearly.
Then probably it might be a local problem. Okay. Let's
Okay.
wait.
Maybe it's my internet then.
It could be, yeah. But I can most probably the recording will be in good shape, so you can have a look later. But let's see. So we just want to see this how variables can develop in time as a function of time. So let's assume we start with 3 viruses at some time t equal to 0, and they multiply by a factor of 2. Then what we can find is that x2 is going to be equal to a squared times x0. x3 is going to be equal to a cubed times x0, and xn, this will be a to the power n times x0. So this is the general equation which is going to describe how the number of the viruses is going to increase. We don't have any other factor which is going to cause the decrease of these viruses. Okay, we are just assuming it's only increasing, but most probably there are biological systems. There are also factors that work against them, but we're not adding that minus sign yet. Let's keep it like this. So let's ask the following question: what is x7? What is going to be the number of viruses at some later time? Now we just substitute here for, we say 2a is equal to 2. We're considering this one after 7 time frames times the x0, which is 3. So here we have 2 to the power 7 is 128. You can correct me if this is not true. Times 3, and this would be equal to 370 and 84. 384. Okay, so this will be the number of viruses. Wait a second, is this correct? Yeah. This will be the number of viruses sometime later on. Now, this is, let's consider this one virus 1. We can have also a virus 2, which they fight together and they affect each other. Okay, so this is how this is going to change. So we are writing here only the dependence of this virus onto its own state. What if there is another effect, external effect, then this could be described minus p times y0. Okay? A more generalized version of the problem could be the following. So we have 2 competing biological systems. Of course, it's going to depend positively on the initial state of the biological system itself. It will depend on the predecessors, on the number of predecessors. It will depend positively, but it will be affected negatively by another biological system that is competing with it. Probably they are competing with regard to the resources of food. So they want to eat onto some host. So that's going to be the equation. So now, these types of equations are very important because they are used. There is also kind of an introduction to the differential equations, which are also very useful. But now, think about this problem. So we represented this one in this way. And the question is, what if the x0 and x1 are not numbers, but they are vectors? What does it mean? That means that we could have a pair of numbers which change as a function of time. So for example, x can be a function of y, but also y might be affected on x. And how can we represent this? We can represent this one as such. We can say xp plus 1 is equal to 7 times xp minus 15 times yt. And this y is also a variable which depends both on the previous values for x and the previous value of y. Okay? So this is our problem. And then given this relationship, what we need generally, what we give here is that we given an initial condition, and this initial condition, it can be equal to 1, 1. Okay? So we can assume initial condition 1, 1, and the question, it will be, this is, let's consider this one, this is equal to x0. So we start with this. The question would be as such, find x4. So find what is going to happen with the number of x and y, which this pair is going to constitute a vector capital X. Find out this generates after some later time. Now to do this, we can reformulate the problem as such by writing the two variables as xt plus 1. I keep making this mistake, yt plus 1. This is a vector, and this would be equal to 7 to minus 15 minus 4. And this would multiply with the xt yt. So here we have an equation, okay? So this is, we are posing this equation, but then we immediately, once we are given this equation, we try to construct the respective relationships in the two different bases, okay? So let's assume, so this is a matrix A. Let the matrix A be here, and this is the standard basis SB. What is the initial equation? The initial equation is this: ut plus 1. This is equal to a matrix A times, no, I said ut. This is xt. This is the first equation. And then we know in linear algebra, we say that if we have such a relationship in this basis, we should have also some other relationship as ut plus 1. This would be equal to a matrix T times ut. Okay? This is capital U. It's a vector matrix, and these are vectors. Then, since we are given here an initial condition x0, we can also write the following. We can say that any vector x, which is composed by a pair of vectors x and y, this would be equal to a to the power t times x0. Okay. Then, if we can write this, you know very well that we can also formulate a problem like this: ut is equal to the dt times u0. Okay, so these are what we can record so far, and then the question is, the question is this: find x4. Let's try to write here what have we given so far. We have given x0, which is 1, 1. This is 1, 1. And this is x0. And then, if this is a given, the question is, well, if we know this much for the standard basis, how much do we know for the new basis? Well, the first thing that we need to know is that in the new basis, what is d? The d, if we solve this system, we have solved this one in the previous session, we will find out that matrix D, it will be represented as what we have written before a while, because 1 and 2, they are the eigenvalues of this matrix A. Okay, this is the matrix A. So the D is right here, and then before we solve this, we say, okay, if the initial conditions are 1, 1 in the standard basis, how do they look like in this basis? So what is U0? This is the first question. So we are asking about this. What is U0? Then we can find it, and to find it, we can. What do we need to find the U0 in the new basis? So
We
albino,
need P inverse.
we need P inverse, that's correct. So first of all, we need the matrix P, and matrix P is equal to, we can remember this, I believe we have solved this before. P is equal to 5, 1, 2, 3. Okay, this is 5, 1, 2, 3. And we need also P inverse. And the P inverse, it will be equal to
-1, -5, 2, 3.
Yes, -1, -5, 2, 3, because the determinant is equal to -1. Okay, so if we have these, then we can say the following. We can say that U0 will be equal to, so we have, this is given, and we come this way with P inverse. This is P inverse times x0, which will be equal to -1, 3, 2, -5 times 1, 1. And this is equal to, we have 2, and the other value is -3. 2 minus 3. So it looks like we start the evolution from the initial condition from a value of 2 minus 3 in this domain. Okay, that's good. And then the question is, how can we find what is U4? Because we are asking here x4. So we're asking here x4. But x4, we can always find it as matrix P times U4. Now, can we find U4? We should be able to find U4 because this will be equal to e to the power 4 times x0, sorry, U0. So let's write it here. So we can say that U4 as a vector, this will be e to the power 4 times U0. So here we have this U0, and this is equal to, what is d to the power 4? 1 to the power 4 is 1. Here we get 2 to the power 4 times 2 minus 3. So this is equal to, what do we get here? Minus 3. No, 2, sorry. This is equal to 2. And the other value is 2 to the power 4. It is 16 minus 48. Okay, so here we have the minus 48. And then the next question is, what is x4? x4, which is the propagation after 4 time frames. This will be p times q4. And p is equal to 5, 1, 2, 3 times 2 times minus 48. And this is equal to 5 times 2, 10 minus 148 is minus 144. This is minus 134. And then we have 4, 2 times 2, 4, minus 48, minus 44. Okay, this is minus 44. Okay, it looks like we found it. So it looks like this value here, this will be equal to minus 134 and minus 44. So this is x4. And we did not write here the u4. u4, this is equal to 2 minus 48. 2 minus 48. That's it. We solved the problem. Now you look how much space you needed. Okay, so this is the solution, and we found it. Okay. So we did not have a single biological system which exponentially increases based on its initial population, but it's a system where we have two variables that depend on each other like this, and it looks like we found a correct solution. So all we needed to do is that from x0, so we can denote the solution also like this. So we were given the x0, okay? We were given here. Then what we did is that we found what was u0. As we said before, solving the system in the better basis is always the best, because this is the mixing matrix, okay? This one, 7, 2, minus 15, minus 4. And then it is best to come to this domain, solve it, and come back this way. So what we do is that from x0, we get the u0, from U0, we generate this in time, so this evolves in time to get the U4, and then we come back, and we get X4. Okay, so this is the standard basis in red, and this is the best basis or the U basis. So this is what we do. X0, U0, we move down with P, and we find this. Or otherwise, we'll have here, so here we move, we can also do this schema actually, maybe it's best if we do that, to make it complete. So we move from X0 with P inverse, okay, then from U0, we move with D to the power 4 to get the U4, okay, and then we can move from U4, how do we move this way? With matrix P. And this here, sorry, we get the, here we get the X4. Yeah. Okay, so now if we look at the schema, so far we just gave the short solution, okay, or we assume it's short because we did not solve the other path. So we start from X0, we want to find X4, and now what did we do? We came this way, we multiplied with P inverse, we multiplied with P4, then with P, we came here. What would be the other path? The other path would be the short one. We can go from X0 to X4, just by multiplying by A to the power 4, right? But we didn't do this. Let's do this, and let's see whether, let's see which one is simpler, which one is a little more easier than the other. And in principle, yeah. So let's see, what is A to the power 4? This is equal to, so what is the relationship between A and D? This one, it's equal, so actually we can do it two ways. We can multiply this with itself again and again, but we can argue that takes, so we can do this 7 to minus 15 minus 4 multiplied by 7 to minus 15 minus 4, and again 7 to minus 15 minus 4. This is still, we have more to do. 7 to minus 15 minus 4. So we can have 3 students and sitting down trying to solve the problem, writing this, doing this, or we can also do this. So we have 3 techniques actually. This is 1, 2. The other technique, which we claim to be a little shorter, is the following. We multiply P, and P is 5, 1, 2, 3. Why is this? Because we can use this part of the board to write down that D is equal to P inverse AP, and A is equal to P, D, P inverse. When I was a student, I always confused these, so it was good for me to write them down on a corner, and I can refer to those. So then this is A4, then A4, this would be equal to P, D to the power 4, P inverse, right? So here we have A4 times, what is D to the power 4? D to the power 4 is, 2 to the power 4 is, what is 16? Times minus 1 equals 3, minus 1.
Professor, I have a question.
Yes.
Can't you just raise all entries of matrix A to the power of 4?
What do you think? Now we did.
I'm not sure, because when you multiply matrices, you do a longer procedure. But I remember that you did that with D to the power of 4.
Yes, but give me a second. So you're suggesting to do here 7 to the power 4, 2 to the power 4?
Yeah, I'm asking, is that valid?
No, it's not.
Okay.
No, it is not, and we can check whether this is true or not. But for D, we can do it because D is easy. Because when we multiply two diagonal entries, this is what you find out. Okay. So you can write it on a piece of paper with diagonal matrices, and this is what we get. So now, so the first approach, it was this, which is shown here in red. The second approach is counting how many calculations we need doing this, and the third one would be this. Okay. Now we claim this to be the shortest. If we think that's the opposite, we can see what we can get from here. So what is a to the power 4? This is equal to so this is equal to 5. We can have here 5, and then we get 4. 2, 16. Wait a second, I cannot see this one. This is 16. No. This is 16, but then this is not 16. This is 48. Sorry. This is 48. Because to get this number, we multiply. Wait a second. We multiply this 53 with this one, we get this 48 here, okay? Times minus 1, 2, 3, 5, and this would be equal to, so here we have minus 5 plus 48, that's 96, 91. Then we have 5 times 3, 15. 5 times 3 plus 5, so it's going to be 51 times 5, that's 252, so this is 255, and then we get 32 minus 2, 30.
Yeah, so that's minus before 5.
Say it again?
Like the matrix minus 1, 3, 2 must be minus 5 according to.
Okay, that's correct. I forgot about that. I copied it. Yeah, it's written here, but yeah. So then we have a couple of mistakes. Let's fix those. So we have minus 48 times 5. This is minus 240 plus 15 minus 225. So here minus 225, and then we have here that 16 times minus 5, this is minus 80 plus 6, minus 74. Okay, so this is a to the power 4, and a to the power 4, this is 91 times 30. I'm sorry, this is 30 minus 2 to 5, minus 2 to 5, minus 74, minus 74. This is the a to the power 4. We multiply this one, let's not forget what this is. This is a to the power 4, right? And we said here that from x0 we can go to x4 using a to the power 4 times x0, which is 1, 1, and this will be equal to 225 minus 91. This is minus 134, minus 134. The first value is correct, and the other value is again minus 44. It looks like it is, we found the same answer, which is this value here. Okay, so yeah. Now I wonder. It looks like in this generation. So do you have any question for what we did so far?
I think it's clear.
Okay. Now we can also. It looks to me that this value here in this domain, this value, the first vector 2, it's always a constant. What if we start? Let's see what we get. If this is 2, 0. Okay. Or is this ever possible? Can we get 2, 0 here? Let's see what. So if this is 2, 0. Let's see what we obtain on this other side. So we do P. Let's multiply the P with the vector 2, 0. And this would be equal to 5, 1, 2, 3, 5, 1, 2, 3 times 2, 0. And this is going to be equal to 5 times 2, this is 10. And then this is 4. second form. Okay.
So the vector is in base D
Say it again.
because we're multiplying with P.
Yes.
Why don't we multiply with P inverse?
Because
Okay, we're going from D. Okay, I got
yes,
it.
okay. Of course you pick that up. That's correct. So apparently this 2, 0 this corresponds to the 10 form. Okay, it's 10 form. Now you can look. You can think about as a small assignment, starting from 1, 1. Okay, starting from this initial condition of 1, 1. Is it possible for that our system will ever go to 10 form? Think about this one. So can we go from 1, 1? Can we ever go to 10 form? But you can consider this one like a XY coordinate system. You start from 1, 1, 1, which is 1 unit from the 0 along the X and 1 unit from the 0 along the Y. Now, can you go to a point which is 10 form? Think about this one. And so more or less, this is the solution given in this case. Now, we can keep this problem a little more general. We can think of it a little more generalized version. And the generalized version would be trying to identify what is xt. Okay? So xt, this would be equal to this, at times x0. So what is at? At would be equal to a matrix, let's say here. So let me put here or to the power, where is it here? Right? This is t, this is t. So at would be equal to p times, what is p? P is 5, 1, 2, 3, times d to the power t. What is d to the power t? The diagonal matrix. I can write it here, d to the power t. This is 1 to the power t, 2 to the power t. This is 1, 0, 0, 2 to the power t, times p inverse. P inverse is minus 1, 2, 3, minus 5. And this is equal to. So we multiply the first two, and the first two, it's we multiply 5, 3 with 1, 0, and we get 5. Then 5, 3 with 0 t, so this becomes 3 times 2 to the power t. Okay. And then we multiply 2, 1 with 1, 0, we get 2, and we get 2 to the power t. We multiply this with minus 1, 2, 3, minus 5, and this is equal. So we get minus 5. So again, we multiply the first row here with the first column here. We get minus 5 plus 6, minus 5 plus 6 times 2 to the power t. And then we have 15, 5, we multiply the first row with the first column, and we get 15, minus 15 to the power t, minus 15 to the power t, we get minus 2 plus 2 to the power t, minus 2 plus 2 to the power t, and then we have 6 minus 5 to the power t. This is 6 minus 5, 2 to the power t. Okay, so this is a to the power t, and then we can say that xt at any time will be equal to, or allow to, this is all xt is always equal to at times x0. So allow me to use here, let me multiply here with a different color, 1, 1. Okay, so what is the answer for xt? If this is 1, 1, we should get the first row, which is here, the first row. We multiply with this column, so it will be simply this plus this, right? So xt is going to be equal to 5 plus, this is 10, minus 9, 2 to the power t, and then we have 4 minus 3 to the power t, 4 minus 3 times 2 to the power t. And this is a vector 2 by 1. So this is the general version, or the general solution of vector xt. Sorry, this is a vector. But this is the general solution if we start from 1, 1. If we start from a different value, then the general solution will be slightly different, because these terms will be mixed differently. Imagine what could happen if we don't have the 1, 1, but if we start, let's say, minus 2, 0. So we could have started at a new value, like minus 2, 0, and the answer will be slightly different. Do you have any question? If not, we can have a short break